Electric motors are one of those things I believe are often worth salvaging from broken devices before recycling them. This one, for example, is universal motor from old washing machine we threw out many years ago. I knew I would find a use for this someday. In this video I will go through what is a universal motor, how it is wired in its original application, and how I am eventually going to drive this one with DC voltage. I have some uses in mind where I need to make this spin at relatively slow speed of maybe few hundred or up to 1000 RPM. Something quite slow relative to the original speed of maybe 15,000 RPM. I received the PCBs for my test circuit in same package with the 3D printed nylon part that I showed in previous video. Both were sent to me by the sponsor of this video, PCBWay.com. In addition to PCBs and 3D prints, they also do CNC milling and much more. The name universal motor comes from the fact that it's universal in sense that it's able to run on either AC or DC. They are used in many household appliances and power tools. Basically, if it works with mains electricity and has brushes, it most likely has a universal motor in it. If we take a look at the small DC motor found in many cordless tools, toys and other battery-powered applications, there's armature with winding in it, brushes and wires for the input power. Around the rotating armature are stationary permanent magnets. Magnetic field of the magnets and the current flowing through the armature winding make the armature spin. This is probably first type of motor people get to know. A universal motor is somewhat similar, but there are no magnets around the armature. Instead, there's iron core and another winding. Magnetic field is made with current passing through that winding, the field winding, instead of the magnets. The direction of armature's rotation depends on relationship of polarities of armature and field winding. In DC motor, magnetic field is constant, so the armature current has to be constant as well for rotation to happen. If armature of DC motor was powered with AC, its current would constantly change direction and the motor wouldn't spin as supposed. In universal motor, field winding and armature winding are both powered from AC. Their polarity will change at the same time. While direction of DC motor can be changed by switching inputs positive and negative leads, switching the input leads won't affect universal motor. In universal motor, direction is changed by flipping either the armature or field winding's polarity, but not both, even when powering it with DC. This washing machine motor was originally connected with field winding and armature winding in series. In that configuration, the same current flows through the both windings. That produces high starting torque, which is especially useful when a motor is started with mechanical load connected, for example drum full of wet clothes in the washing machine. But the current passing through the winding will drop when RPM goes up. That will weaken the magnetic field, which will reduce the torque capabilities. Increasing the load during high RPM can significantly reduce the RPM. If there's little to no load and no closed feedback loop, there's risk of RPM rising high enough for it to damage the motor or something else in the system. That's because weakening the magnetic field will also reduce the generated back EMF, which is opposing the supply voltage. The motor will try to spin faster and faster. But for better torque capabilities in my test application I'm doing something bit different. Instead of keeping the armature and field windings in series, I'm powering them from two different DC voltage supplies. This allows me to have constant current in field winding for better torque throughout the whole RPM range, while still being able to control the speed by adjusting the voltage going to the armature winding. I have selected voltage for field winding by checking current rating of this motor and calculating what voltage applied to this winding will produce current that is close to but not higher than the rated current. Here's how it works. By adjusting the voltage applied to the field winding, we can control the strength of magnetic field inside the motor. A stronger magnetic field, achieved by increasing the field winding's voltage, typically results in more torque. However, this also tends to slow down the motor because the increased magnetic field will increase the generated back EMF, which opposes the applied voltage. On the other hand, the voltage applied to the armature mostly affects the speed of the motor. Higher armature voltage leads to higher speed. With this setup, where the armature and field windings are powered separately, we gain better control over the motor. I can PWM the power to armature to change the speed, but there will be decent amount of torque even at lower speeds. For applications where speed is more important than torque capabilities at changing loads, reducing the field current will achieve higher speeds with reduced torque. That's a quick look at driving universal motors with DC. I am using quite low voltage compared to what it could be run on, because I'm not aiming to achieve anywhere close to the original max RPM. I have included RPM sensor circuit if I need closed feedback loop or RPM reading in future, but for now I didn't need to use that. What I want to eventually do with this is small disc sander for plastics and wood. I need to make a disc where I can glue sandpaper and then attach it to the shaft of this motor. But that's not today's task. See you next video. Thanks.